Now we're going to look at a couple examples of non-linear data. So what I would like you to do now is open up a list and spreadsheets page on your calculator and enter time in one list and air pressure in another list. And it should look like this when you're done. So notice there's time and air pressure. And then turn your calculator back on, or then pause the video and then reopen it for the next step. Okay, now that you have that, I want you to make a scatter plot of the data. So you're going to do Control Doc, open a data and statistics page, and then you're going to go down to the bottom, click on that, add time on your x-axis, add air pressure on your y-axis. When you look at the scatter plot, you can see that it does not appear to be linear, although linear regression would probably give you a pretty high correlation because all the points could be fairly close to a line, but it's curved. You might think it might be a power function, maybe it's an exponential function. Those are two possibilities. So if we go to Menu, Analyze, and number 6, Regression, you'll see that there's a number of different regressions we can choose from other than linear. So let's just try a power regression and see if that is a possibility. So notice this is a power regression with a negative exponent, kind of like an inverse variation function, but that doesn't seem to fit very well. So I'm going to delete that one and try the exponential function. This would also be a decreasing exponential. So using our Analyze and then Regression and then choosing number 8, Exponential Regression. You see that we do get an equation. There's an exponential equation, and it seems to fit the points on the data very well. So I'm going to go ahead and record that equation on the notes in just a minute, but I also want to find the R value. It turns out when you do a regression, so if I go to a calculator page, so I'm going to open up a calculator page now in this same problem. There's a couple different ways I can find the R value. One is just to push the variable button, which is right here, variable button. And notice that it gives you a lot of stat things. It actually gives you, this is the regression equation, here's the R value. All of these values will change every time I do a regression, but for the most recent regression I've done, which is the exponential, this would give me the R value. Another way to get that is to go to your menu and go to Statistics and go to Stat Calculations and go down to the regression, Exponential Regression. So here's my exponential regression. For X list, I'm going to go down and choose time, and then tab down, and for Y list, I'm going to choose air pressure, and it says save the regression equation to F1, that's fine, and then I'm going to go ahead and enter that. Notice here I get all of this information. Here is the regression equation, a, b to the x. Here's a and here's b in my equation. So here's my coefficient. Here's the base of the exponent. Here's the R value that I got before. So notice this, it tells me it's an exponential regression. So I can get a lot of information from here. Now we're going to record this on your sheet, and then we're going to talk some more about this. So if I do an exponential regression, I chose this because of the appearance of my scatter plot. I tried power and I tried exponential, and exponential seemed to fit the best, so that's the one I chose. On my calculator page, I can do menu, statistics, stat calculation, exponential regression, and then I can follow the options, choosing my X and Y lists, and do the regression that way. The equation I end up with is this. Y equals 34.799 times, in parentheses, 0.94933 to the x power. And I got an R value of negative 0.995254. If you just take a look at this equation, I forgot to talk about what this is, what this whole context of this data is. It says the table below shows the pressure in pounds per square inch of a tire at different times measured in seconds after the tire was punctured. So when the tire's 5 seconds after the tire is punctured, it has 27 pounds of pressure left in it. 10 seconds after the tire was punctured, now it's been deflated more, it only has 21 pounds of pressure, and so forth. all the way down to 50 minutes, it only has 3 pounds of pressure. So basically a flat tire at that point. The equation makes very good sense because we have a base that's less than 1, which means we have a decreasing function. Also, we have a coefficient of about 35 here, 34.8. When x is 0, this whole term becomes becomes 1. Anything raised to the 0 power is 1. So y is just equal to the 34.799. So that means when the time is 0, before we've punctured the tire, then the air pressure is about 34.8, which makes sense in the context of the problem. But there's this pesky r value. R is supposed to represent the strength and direction of a linear association between two variables, but this is an exponential association. So why do we get an r value? That's the question. Why do we get an r value? So we're going to do something to the data. We are going to straighten out or linearize the data by using logs. So we're going to start a new column on my calculator list, and I'm going to call it log of air pressure. And I've already done this on my calculator. Actually, no, I haven't done this on my calculator yet. I'm lying. Okay, so rather than call it log of air pressure, I think I'm just going to call it log of air. And notice you can do an underscore by doing control and the space bar next to the Z, log of air. And I typed in log rather than using the log button because I don't want to do a function here. I just want to type in a title. And if you use the log button, it will confuse the calculator. Think you're trying to take the log of something. Now, underneath here, however, in this box, I actually do want to put in a function. I want to put in a function that says this column C is the log of all the values in column B. So I'm going to type in equal, which is under the control, equals, and then I'm going to use my control 10 to the x. Anyway, I'm going to put in log, and then your calculator will automatically do log base 10 if you don't type in a base, so I'm just going to ignore my base right now. Put my cursor inside this parentheses. I want to take log of my variable air pressure. So how do I find my variable air pressure? Well, I could type in my variable, or I can go to the variable button. And when I click on the variable button, let's try this again. When I click on the variable button, it should drop down all my variables. It doesn't like it for some reason. Okay, let me try putting the 10 in. Maybe that's what my calculator is unhappy about. Okay, click on the variable button. Well, it's not happy at all about something. Okay, for some reason when I was pushing on the variable button before, it wasn't coming down, but it came down now. When you push on the variable button, it gives you a list of all the variables, including the air pressure variable, which is what I want. So I'm going to click on air pressure, and it inserts it in here. And then when I push enter, now it gives me the log of all the values in column B. And now I want to find out what do I get when I take the relationship between time and log of air pressure. So I'm going to insert another graph data and statistics page. My x variable now is going to be time, but my y variable is going to be, instead of air pressure, it's going to be log of air pressure. Notice that my data becomes linear. Except for this last little value, it looks like this is kind of where the tire has quit losing air at the end, so these two values were the same, but basically it's linear. So I'm going to do a linear regression on this re-expressed, straightened out data. So go to Analyze, Regression, and I'm going to do a linear regression. Notice when I do a linear regression, it seems to fit really nicely. If I go back to my calculator page and find out what the correlation is for this particular value, so let me find my calculator page. There's my calculator page. And notice my correlation was 0.995254. Now if I go to my variable button, this time when I go down to my stat R, since I've just done a linear regression, this will give me the results of my linear regression. Just to prove to you that that is really from the linear regression, if I go to Menu, Statistics, Stat Calculations, wait a minute, I did something wrong here. Menu, Statistics, Stat Calculations, and I'm going to go down to Linear Regression. For my X list, I'm going to choose time. For my Y list, I'm going to choose log of air pressure, as I did before. And when I do my regression, notice it gives me, here's the equation, the M and the B that I got on my graph. If I go back to my graph, where did it go? There's my M and there's my slope and my y-intercept. And it's not behaving again. Let me try this again. Okay, there we go. And then notice here's my linear regression, and I still get that same R value that I did before. So I'm going to put these values on my notes. When I guess to answer this question, how is this scatter plot different from the original scatter plot? It appears to be linear. Okay, so let's put in the equation that we got when we did the linear regression of time and log of air pressure. Oops, sorry, wrong page. So we got y equals negative 0.022583x plus 1.54157. There's my slope and my y-intercept. And we got the r was still negative 0.995254, which is the same r value we got as we did when we did the exponential regression. So I'm going to show you algebraically why we got that same r value as we did when we did the exponential regression. So what we're going to do is start with the exponential equation. Y equals 34.799 times 0.94933 to the x power. We're then going to take the log of both sides of the equation. We have to take the log of the entire right side of the equation. Whenever you do anything to both sides of the equation, you have to do it to the entire side. Now, I want to make this look like a linear equation, so I'm going to split up the logs on the right-hand side. It's the log of two numbers that are multiplied together. So I'm going to split it up into the sum of two logs, not 0.34. Log of 34.799 plus log of 0.94933 to the x power. Now, using rainbow rule, I'm allowed to bring that x up front. So now I'm going to have log of y is equal to log of 34.799 plus x times log of 0.94933. Now, if you stop for a moment and calculate these two values, you will find that log of y is equal to 1.54157 plus x times negative 0.022583. If I do a little rearranging, I have log of y is equal to negative 0.022583 times x plus 1.54157. Notice that this is the slope and y-intercept that I got when I did the linear equation of x and y, in which x was my original value, time, and y represented log of air pressure. So notice this log of air pressure is this y value. So notice now that what really I'm doing when I take an exponential regression is I'm taking a linear regression of x and the log of y and calculating that r value and then converting back. So your calculator is doing quite a lot internally. So r measures the with an exponential regression, r is measuring the linear relationship between x and log of y. Your calculator is linearizing the data, performing a linear regression, and then converting back to exponential form. Now, I'm going to stop the video now, and I'm going to do the second example a little more quickly on the next example too on the next page. We'll do that on a separate video.